Hello everyone, my topic today is atomic clocks. Atomic clocks are one of the most accurate devices for timekeeping. An atomic clock only has an error of 1 second in a span of 100 million years. So how does such an accurate clock work? In simple terms, an atomic clock uses oscillations of atoms at different energy states to count ticks between seconds. Clocks mark time by tracking a periodic action. A grandfather clock relies on the regular swings of a pendulum. In an atomic clock, the natural oscillations of atoms act like the pendulum. However, atomic clocks are far more precise because atomic oscillations have much higher frequency and are much more stable. The method to achieve this is using atomic beam magnetic resonance. First, the atoms are heated in an oven and bundled into beam. Each atom has one of the two possible energy states. They are referred to as hyperfine levels, but now let's call them A and B. The magnetic field 1 on the left picks out all the state A atoms. Then the state A atoms pass through a resonator where they're subjected to microwave radiation, and the radiation can trigger some of them to change to state B. Then a second magnetic field on the right picks all of the atoms that change to the state B. So the atoms with state changed make it to the detector. The percentage of the atoms that change states depends on the frequency of the microwave radiation. The more it is in synchronization with the inherent oscillation frequency of the atoms, the more atoms change their states. So the goal here is to perfectly tune the microwave frequency to the oscillation of atoms, and then measure it. After a particular number of oscillations, a second has passed. The function of atomic clocks is obvious. They're designed to measure the precise length of a second. The International System of Units defines the second as the time it takes a cesium-133 to oscillate exactly 9,192,631,770 times. This definition refers to a cesium atom at rest at a temperature of 0 Kelvin. So why we need such accurate clocks? Because if you want to measure distance well, you really need an accurate clock. Imagine you're a sailor. You'll need a reliable method for measuring longitude. To find longitude, you need to know the time in two places, the ship you're on and the port you departed from. By calculating the difference between those times, you can get a rough estimate of their positions. So time is important to navigation, and the GPS systems using atomic clocks can be accurate within meters. The development of atomic clocks has led to many scientific and technological advances, such as navigation satellite systems. The accuracy of the systems depends on the proper synchronization of these clocks. A difference of just 1 microsecond can lead to a positioning error of 300 meters. Synchronization must therefore be accurate within 1/100 of a microsecond, and satellite clocks must also be able to function without being adjusted for at least 12 hours. In other words, these clocks must be accurate to less than 1 second error over 140,000 years. Another everyday activity that relies on atomic clocks is telecommunications. When we place a call or send data across network, our information travels by different operators. If the networks are not functioning at the same speed, information may be lost or data highway can become congested. To avoid this, the International Telecommunication Union imposes a standard for operators that limits the difference in speeds between two networks. This accuracy requires 1 second over 3,000 years, can only be met by atomic clocks. The first idea of using atomic transitions to measure time was suggested by Lord Kelvin in 1879. In 1945, Isidore Rabi suggested that atomic beam magnetic resonance might be used as a basis of a clock. In 1949, the first atomic clock was an ammonia absorption line device built at the U.S. National Bureau of Standards. It was even less accurate than existing quartz clocks, but served to demonstrate the concept. In 1955, the first accurate atomic clock, which used cesium standard, was built by Louis Essen and Jack Perry at the National Physical Laboratory in the UK. Since then, atomic clocks have been based on hyperfine transitions in hydrogen-1, cesium-133, and rubidium-87. In 2011, chip-scale atomic clocks became available commercially. It requires no more than 125 microwatts, making it suitable for battery-driven applications. In 2019, the Deep Space Atomic Clock was activated. It is an ultra-precise mercury-iron atomic clock. It is far more stable than existing navigation clocks and would have no more than 1 microsecond of error in 10 years of operations. Most research focuses on making the clocks more accurate and more stable, which led to many competing technologies. For example, scientists are working on something called an optical clock, and it measures atomic oscillations using light from the visible spectrum instead of microwave region. Because the resonance frequency of light waves is 50,000 times greater than the frequency of microwave radiation, the clock will be much more precise. A major obstacle is the difficulty of directly measuring optical frequencies, but this problem has been solved with the development of self-referenced mode-locked lasers. Another example is quantum clocks. A quantum clock is based on cooled single iron confined together in an electromagnetic ion trap. It is insensitive to background magnetic and electric fields and unaffected by temperature. In 2019, such a clock only deviates 1 second every 33.7 billion years. A nuclear clock, however, is still conceptual. It was used the frequency of a nuclear transition as its reference frequency. Such a clock is expected to be 10 more times accurate than the best current atomic clocks. So, what prevents nuclear clocks to become reality? Because for a nuclear clock, direct laser excitation of a nuclear state is a central requirement. But until today, no such excitation has been achieved. The typical energy range of nuclear transitions is order of magnitude above the maximum energy which is accessible by today's laser technology. So we need some elements with the extraordinarily low excitation energy, and considering the nuclear structure, only thorium-229 is promising. The idea was first proposed in 2003, and lots of research has been done since then. Finally, why do we still keep making clocks more accurate? That is because, besides the applications like satellite-based navigation or data transfer, there are potentially new applications. More precise clocks will allow us to test theories like general relativity and allow the search for topological dark matter or the determination of time variance of fundamental constants.